So this next session here will actually cover two libraries. The main focus will be on the hydraulics library, but I will also touch upon the pneumatics library. In some ways, you can say that they're very similar in the library structure, even though it covers two different domains. So my name is Mattias Persson. I'm a Master of Science engineer from engineering physics. I started working on at Modelon in 2008. Okay, so first off, the hydraulics library. So I will cover what you can use the hydraulics library for, touch upon some key features and capabilities. I will also show you some examples of usage. So, and then I will go through the library contents. I will do that briefly here in the slides, but also do a library walkthrough. And I will present some of the main focus of the future development that we have in the roadmap. And at the end, I will also touch upon a little bit of modeling aspects. So if you have the need to build your own models, or if you're sitting and looking at customer models, that can be some key things to think about when you're doing that. Okay, so what is the hydraulics library? Well, the core thing is is a modelical library for simulation of hydraulic systems and circuitry. So it covers components for most of the needs for creating fluid power applications, both mobile and stationary. And if it doesn't cover your needs, there is an extended capability of using templates to build your own building blocks. The main advantage of using Modelon code is also that it's open. You can view it and extend it and modify it in any way. And Daimola also have a capability for model sharing with encryption, which is very nice if you're building subsystems and you want to supply that to a manufacturer or something like that. So the simulation can be for overall system dynamics. It can be testing, verification of dimensioning, or testing control strategies, for example. It's very easy to use. So it's a drag and drop environment. You start with a good set of predefined components. So it means that new users can start very quickly. And but there is no limitations for experienced users. So basically, all components from the libraries are open. They can be copied and modified, and so on. The library is well suited for control design and validation. The nice thing is it fits into the whole multi-engineering modeling, meaning that you can easily combine it with multi-body dynamics, control systems, or even other available libraries like the vehicle dynamics libraries that you just saw. It also has some features with visualization. So I will show you that. It's easier to show you in the demonstrations. But basically, you can see the system behavior animated. So you can see the valves positions. You can see high pressure, low pressure without doing plotting. So you can see it directly in the model. Some key capabilities here is the possibility of integrating the hydraulic system in a wide range of multiphysics applications makes it very powerful. And also the capability of deploying your code, for example, hardware in the loop simulations, or as I will show you an example, for co-simulation, is also a very powerful tool that is available through Daimola. And some list of applications here. We have industrial equipment. This can be agricultural equipment, also construction equipment like drills, hammers, and you see on the right side here is an excavator arm using a hydraulic hammer. It can be for vehicle applications, hydraulic brake systems, hydraulic dampers, gearboxes, power steering. I will show you an example for as well in a minute. For aircraft industry, it can be actuators for the wing flaps, landing gear, folding mechanism, and so on. So there's a whole range of different applications where the hydraulic library is capable of solving a lot of questions. So let me start by just commenting on some recent improvements of the library. We have just had an addition called Hydraulic Elements. The Hydraulic Elements package is the main idea is that so that you can make detailed component design. Many times when you're doing total system dynamics, you're simplifying things here and there, but there is in the hydraulics community there is the need for also doing detailed component design, and this library should cover that. Also, something that we have added are geometry-based restrictions. So normally you parameterize a restrictor by a coefficient, but these new models enables you to use the geometrical shapes to parameterize this restriction. We have also added a complete a whole set of predefined hydraulic fluids. So you can see in the list here to the right is some ISO standard oils that are now available directly to use for the end user. We also have added more oil models, which can, for example, you can have table-based media. You can have unresolved air content in the oil. For example, there is a Nikinen and a Gibson model. And it's also possible now to include hydraulic oils or fluids defined by the Modelica fluids library. So you can, for example, use water content in your in the same hydraulic model if you want to flush the system or simulate something like that. There's also a transmission line model, a long line model. It's very efficient for capturing wave dynamics. Also very efficient for real-time simulation. And we have done a lot of improvement in the documentation, which is of course very beneficial for the end user. Okay, so can I switch? Yeah. So in a second. Okay. So I just wanted to show you a couple of different examples here. And the first example is the excavator. The excavator is a model that is available within the hydraulics library under examples. It's based on an article from the Modelica conference in 2003, so you can see all the details regarding the design and the scope of the model in that paper. It's a nice combination of multi-body dynamics and hydraulics, and this combination in Dymola is very powerful in the sense that you have the Modelica standard library, and it's much cheaper than this combination available through other tools. So this is a good selling point. And so all the non-hydraulic elements are from the Modelica standard library. And I just wanted to switch to Dymola and give you an example here. Okay, so let's open the, let's see here.
Your application
yeah.
showing.
Yep, sorry, we're fixing that. There we go. Okay, so it's possible to see the demo window now. Okay, so let's open the new hydraulics library. Let's see here we go. Let's get it loaded in here. So in the hydraulics library, there is an examples package. I will get back to this in a few minutes. And one of the examples here is called the excavator. So this is the example you saw in the slides. And let's see here. So this is basically the excavator, what it actually looks like. So this is comprised of a multi-body mechanics model for the arms and the bucket and the beam or the boom. And to actuate the motion of this excavator, we're using a hydraulic system. The hydraulic system is actuated by one pump, and that pump drives 4 actuators. One actuator is the pivot around this axis here to rotate the excavator. And then we have 3 cylinders. This one here to maneuver this boom, this cylinder here to actuate this arm, and this 3rd cylinder here to change the angle of the bucket. So let's start by just go ahead and simulate the model and show you what that looks like. So you have in the commands window, run excavator. So let's take a look here at the excavator. So this is the excavator, and what we're doing is testing. We're grabbing something from the ground and we're rotating. Okay, so let's go back to the model. So the problem with this type of hydraulic system is that you only have one pump and you have 4 actuators. Now these 4 actuators have a very different range of constraints when it comes to what kind of power you need to actuate them, but you still need to use only one pump. So for example, you might need 200 bars to raise the boom, while you might need some 350 bars to use the scoop. So so how do you do this with one hydraulic system? Well, so let's take a look at the model. In this mid portion here, we have all the mechanical components. So starting from here, which is the pivoting point. So it's grounded here in the world object. So here we have the pivot where it can rotate. We have the carriage and the boom and the arm. So basically we have from this point here up to this point here, we have the actuating cylinder for the first part. And then between this point here and this point here, we have the actuator for the next cylinder. And the last part over here is for the bucket. So that's basically the multi-body components. So connected through this multi-body components is then the hydraulic cylinders. And these are connected with one-dimensional connectors, meaning that it can only actuate in the direction of the degree of freedom of the multi-body system. So basically, each part here is input signal opening or closing the valve to actuate the cylinder. So these tables here represents the commands given by the operator. And we have this type of system with an input, a restrictor, and a cylinder on all the places here. So this is the same system for the bucket. This is the same system for the arm. And we also have this system here for the swing, so for the rotator. This is a pump, and these others are cylinders. Okay, so the question is, when one subsystem needs to be actuated, you need a certain power output. And when a second system is actuated, you need more or less output, and so you have to throttle the pump, and you also need to make sure that the actuated systems don't get overpowered. So if the most powerful subsystem is actuated, then you might need to restrict some of the other subparts. And this is done in the background in this model here through a restrictor here. So if we go into the modeling layer here, there is a quick and dirty implementation in the equation layer directly here, calculating basically the controls to make sure that we supply the right amount of power to each subsystem. And I'm not going to go through more details than this, but the paper is available where there is a full description. And if we look at the results here, we can see that this is the throttling of the pump. This is the rotation of the mechanism. And we can see here that we have two variables here, pump P max, which is if we're requesting more than the maximum pressure output from the pump, or this pump Q max here, which is the maximum flow output of the pump. And you can see that we hit the maximum output from the pump. So this means that we might need to redesign the control system or redesign the pump for this particular setup. Now, another interesting thing here is also that when you're swinging the excavator like this, for example, this actuator down here, when it's just standing like this, you have a compressive force acting downwards on this actuator. But when you start rotating, you get an outward force due to the load out here, and that's gonna pull it. So the dynamic forces are very different from the static ones. So it's a very powerful way of including the hydraulic system with a correct dynamic load situation by using the combination here with the multi-body dynamics library. Okay, so let's see here. I'm just gonna switch back to the presentation. So this is, you can look at this. It's readily available in the examples package for you. The next is also an example from the examples package, hydraulic examples power steering. So this is a simple power steering implementation for a power steering in a car. Now, this implementation in the library here is with basic components from the mechanics library, but this could easily be integrated into the VDL model as well, of course. So what this model here includes is a custom power steering valve that actuates a cylinder which controls the steering rack. And the boost curve is defined by a polynomial, so you can set the coefficients for the boost curve and try to design a good valve for this, or do some model calibration and find the parameters you need for your example. But let me go back again into the examples and show you that one. So back here in examples, there is this power steering, and it's this example here. So this part up here is the steering wheel input. So this would be the driver input. We have a steering shaft, which is basically the connection between the steering wheel down to the pinion where it's connected to the rack. So the rack is moving translationally, actuating the wheels. So these bodies here you see on the sides, this would be the right wheel and the left wheel. Well, this is all mounted in a rig and connected with some spring damper elements just to fix it. So what you see here, this is the steering input, and at this particular place here, we have the connection to the power steering valve. So this is the mechanical cut basically. So let's take a look inside of this component. So this is the steering input, and this is going down into the pinion. And in between these two here, we have a mechanical spring with an elastic backlash. So basically we can start turning the wheel, and we will deform this torsional spring. Now the deformation here in the spring is an output to the booster. So we know how much lagging we are getting with the relative angle between the rack and the steering input. And this relative angle is boosted by the boost curve. So this is just a polynomial component where you set the coefficients for the boost curve. And if we go back here again, this boost curve then sets the outputs for either actuating the left assist or the right assist. So from here you have the pump coming in, pump port coming into this position here, and depending on if we're actuating a boost to the left or to the right, the fluid is going to go this way or this way. And then depending again on which actuator we're using, we're going to flush the second part. So if we're boosting this side, we're going to flush this side to the tank. Okay, so that's basically how this cylinder is actuated. And if we go into the simulation mode, we can simulate this model. Let's see here. Okay, well, there we go. Okay, maybe like this. So what you see here is just a sinusoidal input, and you can see the rack is moving. We can take a look at, for example, the booster. So let's see the booster in here was called valve gain. So let's search for valve. This one. So Y here is the difference in the steering input and the rack motion basically. So if we plot the outputs as a function of the input, we can see the boost curve. Now we're not actuating it uniformly on both sides. So, but basically this is the equilibrium. This is when we have no deviation in the spring, in the torsional spring. And then when we start moving to one side, we're gonna open the valve to one side and close it to the other. And then when the deviation goes down, it stops and it's in equilibrium again. And then if we open up to the other side, we're gonna open that valve to actuate the other side instead, and then close on the other side. And then when we catch up, we're back to equilibrium. So this is a basic implementation of the booster of a power steering. So this model is also available directly in the hydraulics examples. Okay, so the next example I just wanted to show you. This is I won't show you this in practice, but I will talk a little bit about it. This is a code simulation. So this is where we deployed the hydraulics code and co-simulated it with Abacus. So in Daimola, we built a controller for an ABS system and the hydraulic actuating system for the clamper. And the tire model and the road interaction was modeled in Abacus. And there is a published paper available for this. It's called Interfacing Abacus with Daimola, High Fidelity Anti-Lock Brake System Simulation. And this is also something that a lot of customers request, the capability of co-simulation. And this is also a good example of how you can easily integrate the hydraulic components into a complete tool chain if you're not only using Daimola as a product. Okay, so let's go through a little bit of what we can find in the library. So you can find the typical pumps. There are pumps, motors, and tanks. You have cylinders, there are actuating cylinders. You have double acting, single acting, plunger models. So these can be connected with the translational library. Then you have line models when you have long distance feeding through a rigid line, for example, or a flexible line, a long line, depending on what modeling capabilities you want to capture. You also have volumes, simple volumes, but you also have chamber models for the cylinders, and you have accumulators. There is a couple of different implementation of accumulators. There are spring-loaded accumulators and also gas-loaded accumulators. So let's just see here. There is also a set of directional control valves for flow control. These are actuated by first-order spool dynamics. So basically, you give an input signal if you want to have it in open or closed, and there's a lumped first-order spool dynamics to change the state of the directional control valves. There are other valves which are pressure and flow actuated. Restrictors, laminar, turbulent. It can contain cavitation. It can have polynomial description, and so on. There's also the new hydraulic resistance models, which are geometry-based restrictions. The elements library, which are primitives for detailed component design. There are sensors for pressure and flow, so you can use it in your control or any signal flow models. There's also visualizers, which I will come back to in a few minutes. We can visualize pressure and flow, and also the icons of the components are animated, so you can see the state of the system. But I will show that in a few minutes. And also now the fluids, they have predefined medias. You can have table-based, constant bulk modulus. With unresolved there is Nicknan model and Gibson model. The library contains a standard package order with information, examples, interfaces, and then we have components with two types. So two levels of each component, basically. So the top level component that you would find if you look at the valves package here. So these are then what we refer to as the top level components. These are for the end user. These include volume type models in each connector, and the basic components are subcomponents of these components. But so they can be used as building blocks for creating new user-defined components, and I will show you that in the library walkthrough. So a few words on future development. The most anticipated feature that we're working on is the thermohydraulics. This is under development. So this will include full thermal capability of the hydraulics library. We are also including more primitives to the hydraulic elements library. So it's going to be even more easier to create your own elements.
So excuse me, this is Michael. I have one question here related to the thermal effects, the thermohydraulic library.
Yeah.
Do we so do this cover both? So the let's say the transportation of heat, but also the heat exchange between, for example, the fluid and the outside?
I think right now there is components that take care of local thermal properties, but that's not what I mean here. Here it's energy transport. So if I heat something in one volume, it's going to be transported into the next if there is a fluid flow.
Right. Okay. So is this some kind, let's say, of our partial elements approach?
Sorry, I didn't understand that question.
So is this some kind of a partial elements approach, which means that you divide, for example, your transmission line into small pieces, which then
no, I mean the implementation it's still under development, but I think it's quite finalized. It's going to be equivalent to heat transfer in other fluid models, meaning that if you have a discretized pipe, then of course you have a discretization, but you can have two volumes with a restrictor in between, and if there is flow in between them, it's going to be enthalpy flow through the restriction, and you don't need to discretize it.
Okay.
Does that answer your question?
Yes.
Okay, thank you. And also, of course, our future development plans depend on customer feedback. So if you hear something, if you have the feeling that there is a capability that we're lacking, then we are very receptive to this type of feedback, because we want to help our customers as far as possible, of course. So let me just quickly browse through this, because I see we have not so much time left. So modeling aspects with hydraulics library. This is just a quick and dirty hydraulics 101 if you haven't been working with hydraulics before. So you have pressure, P, and mass flow, M flow. So this is something you will find throughout the models. G is the conductance, which is basically flow resistance. You have the bulk modulus called beta, which describes the oil's resistance to uniform compression. And you will have incompressible flow if beta is equal to 0, and you have compressible flow if beta is larger than 0. And then you have the concept of laminar flow, which is basically a smooth flow, and turbulent flow, which could be described as a rough flow. Each connector contains these two variables, P for the potential variable and mFlow for the flow variable. And every time you connect components like this, you will generate the corresponding equations for that. Some aspects of how you should connect your components. Basically, you have two main component types. It's volume type models or flow type models. So the volume models contain storage of energy and mass. And these are define the states of the system. And the flow type models are restrictors with large gradients over short distances. And these can be algebraic and often generate non-linear equations. So when you connect two different volumes, it's basically saying that you have one volume. And there are some potential risks with that. You might initialize one of them, and then Daimler chooses the second one as a state instead, and then you might get some funny results or non-intuitive results. There's a direct coupling of flow type models. This is basically not recommended in most cases because it can be very problematic numerically, because you generate in between here. You would like to have a state, because to calculate the flow over this component, you have to have the dP, and if you don't have a pressure variable here as a state, you have to have an algebraic variable, and then this can lead to problematic nonlinear systems that can be hard to solve. So this is the main idea here is to try to lump the system in such a way that you connect it with an alternating volume and flow type models. The oil model is a global object, so you will find it in the top layer of all models. It is referred to as keyword oil, and it's a global definition. It is possible to create subsystem with different types of oils, but then you have to separate it in sub structures and define the oil in those subtypes. So that's perfectly possible to create those type of models. Also, normally when you connect components, you start with a source, and then somewhere there's a tank or accumulator. You should be careful with creating closed system models, because there is no conservation of mass in the equations, which can lead to unphysical results. And this is basically the same problem as if you would do an electrical circuit with no ground. So this can be very, very hard to solve. Okay, so that concludes the tutorial, or this one here. And I would just like to briefly show you maybe the animations in here. So if we take this one here, this is a simple cylinder model, which we try to control the position. So we have a commanded position where we want this mass to be located, and we're gonna switch the direction of the flow here to make sure that we actuate this cylinder to move the mass. So let's go ahead and simulate this model. And we can, maybe I'll skip that and just jump directly to what I wanted to show you. So basically here you have the diagram layer in the post-processing view, and if I now animate this here, you can see that all of the icons, or most of the icons that make sense, have an animation. So then you can see the position of the cylinder, you can see the state of the valve, and so on. And this is very helpful when you're doing large-scale system models, because you get an overview of the complete system behavior. That is very, very useful. Okay, so maybe there's not so many minutes left. So maybe we can stop with the hydraulics portion here, and I can just quickly show you some for the pneumatics library. Is there any questions?
Yes, this is Michael again. I have just one question related to the code simulation with Abacus.
Yeah.
what kind of code simulation interface are you using here?
Let me see. I think it was the code simulation interface done through Simulia. So Simulia has a code simulation interface for Abacus. Exactly how that was done, I have to go in and see in the article. But it was a couple of years ago. So, for example, the FMU interface was not available at that time.
Right.
But that also opens up for more types of code simulations.
So, as you just mentioned, FMU, as far now, there's still nothing available which allows you to code simulate Abacus and Daimler through FMI, right?
I would have to refer to Eric here. I don't know myself, but let's see.
I don't think so, not yet. Dog might know even more than I do.
Well, Abacus has a general mechanism to interface to other simulation softwares, and that was used to create an interface to Daimler. So it's a native Abacus simulation interface that was used for this article.
Okay, so is this based on TCP/IP, or do we use any other kind of inter-process communication?
I don't know.
Okay. So, do you know accidentally if there's anything planned on FMI FMU? Because I've got a couple customer requests which are exactly asking for this.
I know that one of the ideas was in the short term to create an FMU interface with, or to create a damper model, for example, for the VDL library, and do that import-export with FMU, just to show the capabilities. But I would have to refer back to John Griffin to see the time schedule he has on creating one of those examples.
Okay, now the people I'm talking to, they especially asking for the code simulation.
Okay.
They would rather like to have some kind of a standard instead of a proprietary interface.
Okay. Yeah, well, I can't give you any straight short answers on that today, but I think we can.
I think we can have a separate discussion about this.
Okay.
Okay. So I would just like to quickly show you. Is this on? This is shared. You see the pneumatics library now?
Yes.
Yeah. Okay. So I will just. This presentation is very similar to the hydraulics. So I will just skip through and show you the most interesting features here. So this is basically the same type of capability as the hydraulics. And what is interesting here is also it's very capable for industrial equipment. You can do brake systems, pneumatic hammers and drills and all kinds of stuff. And to use this for parametric studies. And I would like to show you an example with a customer who have used this library to a large success, a big success. Such a big success that they've chosen that they do not want to share this with anyone else. So I can't disclose the customer or the implementation. But what I wanted to share with you is that they use the pneumatics library to create industrial tool equipment or models of industrial tool equipment. And they did model calibration and verification with existing designs and found that they worked very well. They're using Daimler and pneumatics to analyze system behavior of new designs. They can take it even further than they would normally do to create completely new designs that they wouldn't think of before, to see if it's possible or plausible to do this kind of crazy designs. And they also analyze possible design improvements and robustness of their designs. And one thing that we did that I can mention here as well is we used Dymola and the Pneumatics library in conjunction with ISIGHT to do design of experiment, to do parameter sweeps and optimization. And this worked very well. These Dymola models and the Pneumatics library is very fast to simulate. So you can simulate maybe it was around 10 minutes to do 1,000 rounds. You do it in parallel. So that gives you the scope of the effectiveness of combining the portfolio available through Dassault. Otherwise, I think I will skip this. It's got the similar layout with supplies, cylinders, flow controls, directional control valves, and so on. So you will get the presentation with the full presentation. But I will just switch quickly to the modeling view here, and I will open. Let's see, Pneumatics. This is the Pneumatics library. I will just show you a multi-positional cylinder. So if we go into the diagram layer, this is a multi-positional cylinder. So the idea here is that you have a sequence of chambers, and each chamber has a piston with an arm of different length. So if all these pistons are moved to the left, you would get this position here. Then you can start actuating the first cylinder here to push the whole set into the next position, and then use the different chambers here to achieve a certain position here. And let's see if we just simulate this model. You can also see here this system behavior here. It's opening and closing the cylinders here, and you can do the analysis of the friction in the cylinders and all kinds of stuff here.